like to request him to take the lecture today. One of his style you will appreciate is the blackboard teaching. Of course, it's a whiteboard here with a black chalk. So you will enjoy and appreciate. And usually I love to do that, but most of the time we are now using the slides. But he still uses the handwritten board and explains and derives and everything. So as such, so you will all appreciate. Day-wise lecture schedule is already issued. Minor changes have been made. We'll post it in the group. Deepesh ji, आप post कर दीजिए group में, है ना? So QT-03 group, it will be posted. Minor changes only. Already the schedule was posted. Minor changes we post. So you can take it forward and you can refer it in this thing. You can take it forward, right? So we have been working since I think February 2025. Dr. Ashwath, and he's been taking courses, most of the quantum courses. So you will continue to see him in quantum computing also, and quantum communication, quantum sensing, quantum materials. So all the courses you will have at least few lectures. And quantum sensing, he has taken a major part this time in the MNIT schedule. Initially, there were so many speakers, but finally it was Ashwath sir only who managed most of the content. So we look forward for a good time of, and you will all appreciate the style of teaching. Though it is online, we will try to do it using the written mode, which is very effective for us all to learn, because you can also make your own notes, and he will share the notes also with you in this thing. So that is there. Day-wise schedule not timetable is posted. Schedule something like this is there. This is posted. Please look at that. Day-wise schedule means these are the dates, and these are the topics, and these are the speakers. Okay, so you can look at that, right? Yeah, Ashwath sir, I think enough number have joined, so let's take it forward. Thank you.
Thank you, Pili sir. Thank you so much, and also thank you for accommodating this 2 days. I'm supposed to start on 30 and 31 due to my travel. So I had to request to prepone my sessions for today and tomorrow. I hope it doesn't disturb the other resource persons, also the flow of the content. Yeah, looking at the content, my topics were more of the mathematical physics part. So I don't think any effect on the flow of quantum computing. So it's like a resource for the required quantum computing, whatever I'm going to talk. So let me share my screen and then we'll go ahead. Yes. Yeah. I hope people can see. Yeah, I think everybody can see my screen. Okay. Right. If you want, you can enlarge by removing chat messages. Go to full screen mode. Okay. Right. So I would be using the PPTs wherever possible, and I would use my Blackboard presentation and writing and explaining things. Okay, so I'll also at the same time I would be looking at the chat messages. If there is any doubt, please post your doubt there. I would time to time I would be saying, and I will be clarifying those doubts. Okay, right. Okay, everyone. Very good afternoon once again to all the participants for joining in, and those who are about to join, for them, and later joining people also. Right? Yeah. So as you can see, the title says here, Mathematical Foundations of Quantum Computing. Okay. So the question you can straight away ask yourself, why do I need to study some mathematical modeling or mathematical problem solving in quantum computing? Okay. As you can see on the right side, a mathematical foundation, something like dealing with some functions. Okay. Right. So dealing with some function, some f of x sinusoidal function. Okay. So when it comes to quantum computing, what are we going to do? We are going to create some quantum states. Okay, basically quantum states, you might have by now what you have seen, the quantum states are represented by wave functions. Okay, I'll start with the, yeah, I can't enlarge anymore. I am, yeah, Arunimaji is asking, please enlarge. This is the maximum I can enlarge. What you can do, you can go to full screen mode in your laptop or in your setup, PC. Then you would see full. Okay, right. Yeah. Fine. So there you will start with some system which is in the ground state, and then you evolve the system to become some quantum wave function. Okay. So during that, you are actually letting the system to evolve dynamically due to some environment effect. So there, how this system is evolving in time, it is represented by a dynamical differential equations actually. So we need to know how this differential equations has to be solved. So that's why we need to understand the mathematical foundation of differential equation solving, whether you do numerical integration or whether you do analytical integration on paper. Okay, that you should know. So that's why we are getting into this domain. Okay, right. So straight away, if you see how and where are we getting this differential equation. Okay, right. Okay, so they're saying I can't have anything enlarged more than this. Okay, right. The layout section, since I'm going to write, so I would not get, but don't worry. Yeah. How to get rid of that layout? I don't understand. Let me see. Yeah, I don't see anything other than, yeah. But don't worry, I'll explain. Okay. Yeah. Fine. So now, so there are two ways I can understand about the quantum systems. Okay, let me go back and use hand notes. Okay, so hand notes means this is my hand notes. Let's say I take a qubit. Okay, let's consider a qubit. Okay, how do I consider a qubit? Qubit could be quantum system represented by alpha 0 ket, beta 1 ket. This is a qubit. Okay, so on paper I am represented as a quantum ket state. Okay, right? So the quantum ket state is represented. So in reality, what is this? In reality, this is an electron confined to exist in ground and excited state. Means it is actually doing a hopping between ground and excited state continuously. It's like a coin being tossed. Okay, right? Now that is the state of the system. Now that system is confined. Let's say it is confined in a small box. Nothing is there inside a box. Or if something is there inside a box. Okay. Let's say if something is there inside a box. In that case, this electron is going to have some kinetic energy and potential energy. Okay. So electron confined in a box. Okay. Example is an electron. Electron confined in a box. There, what is the total energy of the electron? So total energy of the electron would be some kinetic energy, some plus some potential. Potential energy means it is surrounded by some space, and the space is consisting of energy coming from some surrounding other charges, let's say. Okay. So now kinetic energy is usually represented by half mass of the electron into velocity of the electron, half mv square. Potential energy is some potential energy u, or maybe let's say v. let me use a V because U is reserved for unitary operator in our case. So this is the total energy of the system. Okay. When I talk in real life, this is how I write the total energy of the system. But when it comes to very, very smaller level, atomic level or electron level, so the operators, sorry, the energy which are represented, okay, involves some variables like a velocity, kinetic energy, half mv square is an operator or some kind of a observable I can measure and find out. These things actually becomes something called operators, some kind of a derivatives. Okay, so this is actually covered as a part of QT-01 and 2 for you people. If somebody has some doubts, for them I'm just giving this description so that it is more complete. Okay. Okay, right? So now if this is a same half mv square, I just convert that into multiply by m divided by m. It becomes m square by m square into v square by 2m plus some potential energy. Okay. So by the way, linear momentum is mass into velocity. So p square is m square into v square. Okay, so the kinetic energy is p square by 2m plus some potential energy. This is total energy of the system. So total energy of the system, when it comes to quantum systems, total energy is represented by Hamiltonian, which is going to represent it as a Hamiltonian hat. Okay, H hat. H hat is potential energy hat plus kinetic energy hat. Hat, the moment I put a hat, pointy hat, means it has become an operator. Okay, so the potential energy, kinetic energy consisting of linear momentum operator P, which is minus IH cross dou by dou x if I am talking about linear momentum in the x direction. If I want linear momentum in the y direction, it will be minus IH cross dou by dou y. And linear momentum in z is minus IH cross dou by dou z, derivative with respect to x, y, and z. Okay, so the H is an operator, total energy. H operator acting on some quantum state psi of x. Let me neatly write down that. H acting on psi of x gives you same psi of x state multiplied by some E, eigenvalue problem. So where E is the energy. Okay. So now the question is, if H becomes an operator form, okay, what would be the operator form? Let's say I will only talk in terms of x dimension. Means the electron is confined only to one dimensional motion. Okay, so x is equal to 0, x is equal to 1, L. So this is 1D box. In that case, the kinetic energy is p square by 2m is simply minus IH cross whole square, okay, px square by 2m. Okay, so this is a p square by 2m. So what is, sorry, I'm very sorry. This substitution we are going to do. Okay, minus IH cross whole square dou by dou x whole square by 2m. So which is going to give you minus h square dou square by 2m dou square by dou x square. This is a kinetic energy operator form. So potential energy, let's say I don't know explicitly what is the potential energy. I'll just keep it as it is. If somebody wants, they were saying, I literally want to know, okay, what is the kinetic energy? Okay, for you people, let me explain what is the potential energy of the system. Okay, so when I have an electron inside a box, if I disturb the electron, what it does, it creates some kind of a oscillation, some kind of a vibrations. It is just like vibrating. It's like energy vibrator. Okay, so if you just go and drop a stone in the lake, it is going to create a ripples. It's like kind of a oscillations. with the way I am speaking, I am creating a disturbance. So this disturbance is traveling. Okay. So likewise, the electron is there. If I give small energy, it creates a vibrations, some kind of a disturbance. It is just equivalent to, or analogously, it is equal to a pendulum being disturbed. Means pendulum means it wants to stable, it want to stay in an equilibrium state. But what it does, the moment I just disturb, it makes an oscillations. This is one example. Another example, let's say you take a spring mass system on some frictionless table. Let's say I have a spring mass system where spring mass is m, spring is some k, spring constant. If this system is there, okay, now the moment I stretch the spring is rigid, it tries to come back. It come back and goes to the old position. Since it's unable to stay in old position, it just gets compressed, it makes an oscillation. This is just equivalent to a vibrating, oscillating pendulum, as vibrating oscillations for spring mass system. So in this case, if you see the potential energy of these systems is simply equal to half k x square. Okay, straight away I give you an equation. What is half k x square? Okay, and see the question you can ask me, in the case of spring mass system, I understand k coming into the potential energy. But in the simple pendulum, what is k? There is no spring constant. What is k there? Let me tell you. The k there is, in the case of spring mass, in the case of pendulum, k is, okay, omega square is k by m. Okay, literally angular frequency of oscillations square is equal to k by m, where k is equal to m omega square in the case of spring mass system. Similarly, in the case of pendulum, if there is any rigidness is going to exist, some kind of a restoring force is going to exist, that is represented by the spring constant k. So that spring constant is actually equal to m mass of the system multiplied by angular frequency square of the system with which it is going to oscillate. That's all. If I know the mass of the system, if I know with what angular frequency it is going to come up with, and I just multiply them as m omega square, I can find what is the spring constant. So therefore the spring constant of a pendulum is just k equal to m omega square. Okay, it doesn't need a spring, but still it can have a rigidness. Okay, the restoring forces comes with because of the rigidness of the spring. Similarly, the pendulum is always trying to come back into stable position. You know why? Because of the gravity. Gravity is creating that kind of a spring motion. Okay, gravity is trying to bring the spring to the the pendulum to the stable position. So that is the rigid force comes because of the gravity. So there is a spring constant. So kinetic energy is half kh square for a pendulum. Oscillatory electron is like a pendulum. So what is the potential energy of the pendulum? Potential energy of the pendulum is, okay, so potential energy of electron being represented by a harmonic oscillator. Simple harmonic oscillator also people call, means just like a pendulum, is going to be half kx square, where k is m omega square. So the potential energy in our case is half m omega x hat square. Okay, a position becomes a position operator, x becomes x operator. So when it comes to operate on something, it just multiplied by x. So x doesn't have a derivative operator, only kinetic, only linear momentum as a derivative operator. Okay, there is one more operator form exists in quantum computing, which is energy. Okay, so Hamiltonian acting on the quantum system is equal to energy operator acting on the quantum system. Okay, now sometimes H is not going to take its operator form, E would take the operator form. Okay, what is its operator form? E is IH cross dou by dou t, time derivative. When it takes a time derivative, H is going to remain as a matrix. H is represented by a matrix consisting of system and its surroundings. Okay, so in that case, what happens? It becomes, this becomes E psi is going to become IH cross dou by dou t psi, okay, is equivalent to H psi. Okay, so this is a differential equation for you. I need to solve this differential equation. We need to solve the differential equation to know about how is the system is going to evolve in time. So basically, how do you solve this? We have done it already in your QT-01 and 2. For somebody who has not seen, for them, let me solve for a few minutes. Okay, let's rearrange this as dou psi by psi is equal to H, okay, divided by IH cross into dou t. Okay, so if you just integrate the entire equation, let's say from psi naught to psi final, some t0 to t final. Okay, so this would be a log of psi. If I substitute psi phi minus psi 0 is equal to H, I can, let's say it is time independent, means it's not dependent on time. Okay, so in that case, I can just take it outside. Explicitly, I have not written H is independent of time. Okay, so this will become minus I by H cross integration of T naught to Tf dt. Okay, so partial derivative dou t becomes dt here. So now left hand side is log of psi f by psi 0. Right hand side minus IH cross Hamiltonian into TF minus T naught after integrating. Okay, so what I will have, send the left hand side log, natural log to the right hand side. Psi f by psi 0 is equal to exponential minus IH cross Hamiltonian multiplied by T final minus T initial T naught. Okay, right? So quantum state final is equal to quantum state old multiplied by exponential minus IH cross Hamiltonian T final minus T0. Okay, so this is not a function, it's like multiplication. So by knowing the old value, I can find the new value. How? I just multiply it by some factor. Okay, so this factor, when I multiply, when I send the left hand side to the right side, it should come here, not on the left hand side. So let me do this. Okay, so basically what is this exponential term? The exponential term is actually called unitary operator U. It's a unitary operator. Okay, why it's called unitary operator is, if you just take U multiplied with U dagger, you are going to get identity. You can see it from here itself. By the way, so U is exponential minus IH cross H into T minus T into T minus naught. Let's say T final is some T. Okay, right? So Hamiltonian is Hermitian operator, means H is always equal to H dagger. Now you take a U dagger, what is happens? It becomes plus IH cross H into T minus T naught. When you multiply, okay, when you multiply U into U dagger, what happens? You are going to get exponential minus IH cross, okay, T minus T naught, exponential plus 1 by H cross H into T minus T naught. You see? So one is positive exponential, another one is negative exponential. It is going to cancel. So you're going to get identity. One, it's an identity matrix. Okay. So you see, it's a unitary operator which tells me how the evaluation of the system happens in the form of unitary operator. Okay. So let's get back to our presentation and just quickly see what I was referring earlier. Basically, a system is being represented by eigenvalue equation. Okay, eigenvalue equation, or people even call master equation. Okay, so this describes how the system evolve. Basically, when I take H into some operator form, I have a differential equation. When let's say H remains as a matrix, E takes an operator form, I'll have differential equation like this. Okay, so E taking an operator form in terms of time, it is called time dependent Schrodinger equation. When E remains as it is, H takes an operator form, which we will be discussing in later case. So there we will have Schrodinger equation in space. Okay, so that becomes a time dependent Schrodinger equation, independent Schrodinger equation. So basically, in short, it is written like this. Explicitly, we will see in the later slide. Okay, so this is what I meant. So there involves a second order differential equation, you see, right? So I had written here straight away a particle being in a box and a quantum harmonic oscillator. Okay, so let me explain what I mean by that. Okay, right? So first of all, okay, so energy of the system, energy of quantum system. Okay, how do I represent energy of the quantum system? Okay, with a Hamiltonian, which is going to be potential energy operator, kinetic energy operator. Okay, so by the way, kinetic energy operator is momentum operator square by 2m. Potential energy is half m omega square x operator square. This is a kinetic energy. Okay, okay. Somebody was saying, Srikandas Soumyaji is saying it is very difficult to follow in one go. So please share the notes. Of course, I'm going to share the notes. Don't worry. Okay. So I'm going very, very slow. Right. So I just want to know how the system or a quantum system behave in time. So let's say I take a glass of hot water and keep it on a table. After some time, what happens? I see some kind of a sublimation of outside a glass. I see small drops. Okay. So what I see is the temperature of the water is losing to the surrounding, and the temperature around is obtained or acquired by a water particle in the air, and they are going to become water and going to stay on the glass. So basically what is happening, the temperature of the hot water is losing to the surrounding. Okay, now the hot water being very hot in the initial stage, losing the temperature, evolving in time. Similarly, when I take a quantum system, I leave it at some point into some surrounding, it is going to change its nature depending on the surrounding. If I just take a hot water, keep it at a very cold temperature, it loses the temperature in a certain phase or certain speed. When I take a hot water, keep it at a very, very hot room. So in that case, it loses temperature in a different rate. Okay. So depending on the surrounding, system is going to change. Now I am going to write down what is the energy of the system in terms of its kinetic energy and potential energy. That is the only two energy forms any system can exist with. Okay, right? So the total energy of the system is like this. Now a quantum system is going to have a quantum state form psi. Okay, in eigenvalue and eigenvector equation, usually, okay, eigenvalue equation means eigenvalue equation means what? A matrix is there, multiply onto its eigenvector is going to be going to give the same eigenvector with some eigenvalue multiplied. Where for the matrix, E's are eigenvectors, okay, and lambdas are eigenvalues. Okay. So interestingly, when it comes to quantum systems, H is a matrix which represents the quantum system as a matrix, and the quantum state sign is a eigenvector corresponding to that H, and E is energy, eigenenergy of the quantum system. Okay, H psi is equal to E psi. Now, for me, H psi, sorry, H is represented by this form. It will become time independent Schrodinger equation. What is that? P square by 2m plus half m omega square x square multiplied by psi is equal to E psi. Okay. Now what I'll do, I'll send E psi to the left hand side and explicitly write down what is a P. Okay, 1 minute. Just a minute. Okay, continue. Okay, okay, this turn off. Yeah, right. So I just clicked something. Okay, so P is P square is minus, let's say I'll confine to the x dimension, minus h square dou by dou x whole square. Okay, so in that case, what I'm going to have minus h square dou by dou x square by 2m. This is my kinetic energy term. Half m omega square x square is a potential energy term multiplied by psi is equal to E into psi. Okay. Now let me rearrange this for more simplest case. So what is that is multiply the entire equation by 2m by h square. Okay. Or even you can multiply with the minus 2m by h square. Okay. Right. Just for the simplification, what do I get in that case? Dou square by dou x square minus 2 gets cancels. I'll get m square omega square x square by h square into psi is 2m e, okay, psi divided by h square with the minus sign. Okay, so let's send to the left hand side. Okay, so what I'll have dou square by dou x square plus 2me divided by h square minus m square omega square x square by h square whole multiplied by psi is equal to 0. So this is the differential equation I have, second order differential I have, which represents how quantum system is evolving in time when I know H explicitly in terms of kinetic energy and potential energy. This is what I have it in my expression here. Okay, on the right side. You see, and even I have taken 2m by h square outside, but in the, okay, let me write down even that for your convenience. 2m by 2m by h square, if I just take a common, what I'll have E minus, okay, m omega square x square by 2, okay, h square into psi is equal to 0. I hope this is the expression we have it here. Absolutely. M omega square x square. Okay. Just a minute. H square is not there. H square already came out. Fine. So you see now m omega square x square is a unit of energy. That also makes sense. Subtracting from energy, some unit of energy has to be subtracted. That is also, it's a potential energy, by the way. Half m omega square x square is a potential energy term. Okay, right? So now I have to solve this differential equation. By the way, there is a psi here. I forgot to put the psi. We should not miss the psi. Okay. So the differential equations are involved here. Second order differential equations involved. By the way, I should know how to solve it. That's why we need to study the solving differential equations. Okay. Now, the specific case, I have a particle in a box. On the left hand side, I did not write any kinetic energy, any potential energy part at all. What is that is, let's say particle is confined in a box, there's nothing else in the box. It's like absolute vacuum. Okay, so there is no way there is some kind of energy comes from the system which disturbs the system to create some kind of a vibrations. Okay, what I mean in that case is, okay, there is no angular frequency at all. There is nothing else to have that kind of a vibration. So in that case, what happens? The second term, this term is going to disappear. So what I'll have, when the particle is exist inside a zero potential. Okay, zero potential in the sense V of x is 0. What happens in that case? About differential equation becomes simply dou psi by dou x square plus 2me by h square into psi is equal to 0. Okay, so now if you look at this differential equation, it's second order differential equation and it's also linear differential equation. What I mean is, if any derivative is directly proportional to the function as it is called linear differential equation. Okay, so the above differential equation is second order differential equation which is linear. Okay, so these linear differential equations actually possess exponential solutions. We will see that what is the exponential solution. Okay, right? So here in this case, for simplicity, what I can do, I can define a variable k. Let's say, define a variable k. We already use a k for spring constant. Let's say this is a k energy, or it's actually propagation constant, units of propagation constant, which is 2me by h square. I think, yeah, I think it's k square. K square is 2m by h square. So what is a k? K of e is square root of 2m by h square. Okay. If I do that, what happens? I'm going to get a differential equation like this. The particle in a box. Now, this particle in a box, if you solve, it is going to give you some energy states having energies which is going to have some exponential expression like this. Okay, so for your convenience, let me solve for you. So what is the differential equation I have? Dou square by dou x square plus k square multiplied by some psi of x is equal to 0. This is the differential equation I have. Okay, if you want, for your own sake, let me write down that as, okay, right? Forget about what is k. Okay, so this k is energy k, is a propagation constant, not a spring constant. Okay, now how do I solve this differential equation? So it's a linear differential equation. what you usually do, if such situation exists, you can simply guess this psi of x is some constant exponential of some mx. Okay, I can later find what is the m. If you are not comfortable using m because m is being used for mass, some ux. Okay, so you can find that ux by substituting this into differential equation. You can find. Remember one thing: the quantum systems are of unit length because the total probability of quantum system is 1. So you can simply ignore even a amplitude. Amplitude is going to be 1 always. So you can just ignore that. So which implies a is equal to 1. Okay. Now, when I just look at this differential equation, you can straight away write down the solutions are some k sine into kex. Okay, some sine kex. So solutions of this differential equation. So these are sinusoidal solutions. Okay. So when I take a particle inside a one-dimensional box, so it can go either side up to x is equal to 0 to x is equal to n. Remember, the particle is a quantum particle. It is existing inside means it is going to execute some kind of a wave nature around. So the wave nature means it's a kind of a disturbance is traveling. So that disturbance is traveling is like a sinusoidal wave. So like that. Okay. Interestingly, at the edges x is equal to 0 and x is equal to n, this function should go to 0 because the particle cannot exist at the edge. Okay. So the boundary condition here is psi of x must go to 0 at the boundary. Okay. So there are two boundaries here. One is x is equal to L. So the quantum state at x is equal to L must be 0. Since it's a sine function, it is taken care. But when psi is equal to psi at x is equal to L must be 0. What it implies? It implies kx into L must be 0. Sorry, kx into L sine of kx L into 0. Okay, sine k, not a kx, let me say ke into 0 is 0 anyway. But when it comes to x is equal to L, sine kl, sine ke into L is 0 implies what? Ke into L is some n into pi, integral pi value, where integer n can be starting with 0. In that case, I'll have 0. Okay, right? Otherwise, I can have any values other than 1 pi, 2 pi, and so on, any higher pi's. Okay, right? So this implies, okay, so KL is equal to n pi captures every other situation. So I can write down what is the solution of this quantum system. Wave functions sine n pi into L. Okay, sorry, let me write down. Okay, Ke into x, where Ke is n pi. Okay, so what is the corresponding energy? Earlier we saw K E square is 2m, okay, 2m E by h square. Okay, so which implies the energy is Ke square h square divided by 2m. I just found what is a Ke. Ke is n square and pi. Okay, so energy of the various energies of the quantum system is n square, pi square, h square by 2n, where n is an integer starting from 0, 1, 2, and so on. So it is just like electron being existing at ground level. Okay, electron existing at n equal to 1, n equal to 2, and so on in the hydrogen atom. Okay, so that is what I have in my expression. So K energy is n square pi square h by 2m. I think I missed L somewhere. Let me capture that. Okay, KL, yeah. Okay, L square. Fine. So that is what I have in my expression systematic. Okay. Now, let's say I know explicitly what is the potential energy around. I'm not only talking about electron existing in zero potential energy, it is existing in some potential energy. There, this potential part is explicitly write down half m omega square x square. In this case, you know what happens? The energy is no more going to be a single entity. It is going to be some h omega multiplied by n plus half. What I just told you earlier, the moment potential energy comes into the picture, what happens? System starts vibrating with some angular frequency. That has to be captured inside. The moment some angular frequency is there, as you know, frequency multiplied by Planck's constant gives you energy. So that is what h omega correspond to some energy of the system. Just like a photon, electron is going to have some energy in terms of it's a wave consisting of some angular frequency or wavelength. So from that you can calculate what is the corresponding energy. Okay, so now let's take that. If the particle is confined in a potential, what is the potential? Here it is given as half m omega square x square. Okay, potential is defined in terms of the spring constant K, okay, where the spring constant here is m omega square. Okay, so in such cases, if particle is confined in such potential, it is going to create, okay, a kind of a pattern, like a wave pattern, like one single wavelength confined. So this is going to correspond to n equal to 0 and n equal to 1, okay, and so on, n equal to 2 wavelengths, n equal to 2. Okay, so how do I know this wave natures? Basically, you can solve this differential equation, okay, this differential equation explicitly for the final solution. You see, the only difference between this equation to the equation which we solved, only the extra factor is coming inside the K. Okay, what you can say is, you can say the new differential equation in the potential case is dou by dou x square plus, this time I'll just say K with potential energy K square entire equation multiplied by psi of x is equal to 0. Okay, the expression like the form remains same, second order linear, but only the K actually changed from Ke to Kpe. Earlier it was only kinetic energy, now I have also added a potential energy. In this case, the solution still be sinusoidal. It can be sinusoidal. Okay, so these solutions this time what happens? Okay, it is going to have energy values which is going to be h omega, okay, n plus, where again n is integer 0, 1, 2 and so on. Okay, so the quantum states, if I want to explicitly write down, so those things, okay, so in one case I have one wavelength confined within x is equal to 0 to x is equal to L. In another case, maybe 2 wavelengths, maybe 3 wavelengths, maybe 4 wavelengths, and so on. How do I find the particle's location? Just take the absolute square of the wave function This will give particle location. Okay. So you see now, solving the differential equation, I'll get to know a lot of things in quantum computing. Okay, right? So now let's go further. What else I would say, right? Now, let's say take a hydrogen atom. Hydrogen atom, what happens? Okay, in the hydrogen atom, there is a nucleus. There is an electron. Only single electron is there. Okay, the single electron is revolving around the nucleus. Okay, right? So single electron is revolving around the nucleus, and not only it's just revolving around the nucleus, about its own axis it is rotating. You see, there's rotational dynamics also. There is a spin dynamics also into the system. So I need to capture all of them into the dynamical description. Okay. So to do that, let me remove this. Okay. Let me write down. So what are the things are involved in hydrogen atom? Let me write down. Hydrogen atom. Okay. In the case of hydrogen atom, if you just say nucleus is there, electron is revolving around the nucleus. Okay. Who is giving the possibility of electron to rotate about the nucleus? It is a Coulombic force of attraction. Okay. So what is a force? Coulombic force of attraction is 1 by 4 pi epsilon naught charge of the nucleus multiplied by charge of the electron divided by r square. It is acting along the radial direction. Okay, right? So there is a question. I'll quickly come to the question. Give me a few minutes. Okay. So Coulombic force of attraction is this. This is going to give the what it does. It ensures the electron revolves around the nucleus in a particular orbit. So this Coulombic force attraction is going to create some kind of a groove around the nucleus. It's like trenches being built around the forts. You see, olden day kings used to build the trenches around their fort. Okay, why? If some enemy is going to come, they have to, while coming, they may fall into the trenches. That time, these people will attack. So nucleus is created some kind of a trench around the nucleus, so that electron exists in that trench. It doesn't goes anywhere. So in order to go anywhere outside or coming close to the nucleus, somebody has to do that. Who has to do? Some external means has to come with some energy, give the energy to the electron to come out of the trench and go somewhere else. Okay, so somebody has to act against that Coulombic force of attraction. Okay, so this Coulombic force of attraction creates a potential energy. Okay, how to find the potential energy created out of this Coulombic force of attraction? Very simple. So there is a connection between force to change in potential energy. Okay, so if I have to change the potential energy, okay, with respect to some distance, it is going to create out of some force in a negative way. So the force is always equivalent to rate of change of potential energy. So by the way, I know what is the potential force, that is 1 by 4 pi epsilon naught. So energy of the nucleus and energy of the electron both are same by magnitude. Let me take that E square by R square. Okay, right? So what I will do now, let's say du is equal to 1 by 4 pi epsilon naught. Okay, there is a electron charge is minus sign, so minus sign and minus sign. Okay, so there is a minus sign, minus gets cancelled. 1 by 4 pi epsilon E square 1 by R square dr. Okay, now let me integrate. When I integrate potential energy as a function of R, you are going to get E square by 4 pi epsilon 1 by R. So this is a potential energy term. If I had missed minus sign, we will see in the later case. So potential energy I just found from the Coulombic force of attraction for a hydrogen atom. Okay, so that is one. And electron revolves about itself, that is a spin. And by the way, when electron revolves about the nucleus, that time it is construed as something called a DC current. Okay, so it's just like a wire being bent in a circular fashion. Okay, so because of that, it becomes some kind of a solenoid. It creates a magnetic field along the axis. So a current carrying wire creates a magnetic field along the axis. It is called a magnetic moment. Okay, so that also has to be captured. It is going to come as a linear magnetic moment. So that is comes in terms of some magnetic quantum number. Okay, so what else is there? I have in this case, I have potential energy, which I just derived. I have kinetic energy, the actual energy term. Okay, and there is a spatial derivative because of potential energy, sorry, kinetic energy. And in this case, I see a derivative with respect to r. Earlier, I have only derivatives with respect to x. This time, I have a derivative with respect to r only. This is actually, this equation is a spherical coordinate system. Okay. So in this case, what are the coordinates I am going to have? I am going to have r cap, theta cap, and phi cap. Okay. So the second order derivative in r actually comes with 1 by d square by dr plus 1 by r into 2 by r into d by dr. Okay. What I mean is, see, in Cartesian coordinate system, the second order derivative is, okay, save 1 minute. Okay, in Cartesian coordinate system, 1 minute, quickly I'll go there. Yeah. So this is dou square dou x square plus dou square by dou y square, dou square by dou z square. If I am only writing in x term, this is dou square by dou x square. So correspondingly, this second order derivative for radial direction is d square by dr square plus 2 by r into d by dr. Okay, so this is a corresponding second order derivative in radial direction. That's why you see two terms here. And these two terms, this is corresponding to energy, this is corresponding to potential energy. This comes because of angular motion of the electron around the nucleus. Okay, so this is a hydrogen atom differential equation. Again, this needs to be solved. Okay, so we need to go for finding the differential equation solving method. So I hope now you understand why quantum computing seriously relies on ordinary differential equations. Okay, so let me quickly go for a questions here before giving a break. Okay, let me see, is there any questions? Okay, there may be somebody is saying p only, not p square. Maybe I had corrected it. Is it whole psi? Yeah, psi means, okay, this is a psi, quantum state psi. Okay. Okay. Let's see. There is a question by Jagdish Neela. Is there any meaningful connection or useful analogy between this macroscopic discharge process and concepts used in quantum computing? For example, superposition, tunneling, collective quantum effects, or decoherence. Or is lightning essentially a classical electromagnetic phenomenon with no direct quantum computing relevance? Okay, there is a meaningful connection between this macroscopic discharge process and concepts in quantum computing. Of course, we are trying to answer that question because we are going to talk about quantum qubits. When they are exposed to the surrounding, they change their form. Okay, how they are going to change their form, how to address that, how to define that. I'm not only going to like experiment every time. I need to come up with a mathematical modeling that captures everything. So, how to define that mathematical modeling in terms of differential equation? That is what I was trying to do. I just earlier I gave you a situation where a quantum system means a qubit or an electron confined in a space, there is nothing else in the space. In that case, what is the solution of that quantum system? Okay, right? And with what energy that system would exist in? Okay, let's say it is confined in a potential where I know what is the potential energy. In that case, what is the corresponding wave function would look like? So that also I should find out. So there is a connection, whatever you are talking about, to the quantum systems. Okay, right? Okay, now let's see electrostatic. Yeah, the electrostatic Coulombic force is involved here. Okay, whatever you are writing, is it not visible on the screen now? I think you should check. Arunimaji, please check. I have opened in another system. I'm just looking at whether I am my display is visible or not. Okay, fine. So we'll just take a quick break of 5 minutes and we'll continue from here. And I'll conclude after that. Okay. We'll come back at 4:10. Yeah, welcome back, everyone. Yes, there were a couple of questions were asked. Will there be a course on open quantum systems in future? I don't think so, a specific a course, but there will be topics which are going to talk about the quantum systems being open to environment, okay, to interact, and the quantum systems were absolutely closed. So the moment you have open quantum systems, there will be a chance that environment going to create a noise that is through decoherence. So how to tackle that and how to address that, how to understand this noise, how to mitigate this noise. So it is all about quantum error correction or quantum error mitigation. So in that case, you would explore these things. Okay, right. I would have a okay. I would love to have a course on open quantum systems. Even few specific lectures would be great. Yeah, I think it will be covered somewhere in this QT's modules. Is there any testing tools available for testing quantum algorithms? As such, there is no testing tool, but what you can do is you can start like use a conventional classical algorithms on a particular data, okay, and you do some kind of a classification, let's say binary classification or any ternary classification of the data, and see how much accuracy your algorithm is giving, and immediately on the same data you can have a quantum analog algorithm for doing that same binary classification. Okay, so there's for every classical algorithm there is a counterpart in a quantum algorithms or quantum computing. You can use them and compare them and see how well you are coping up, your algorithm quantum algorithms are coping up. And here there are two things you have to remember. One is your computing capability. Okay. So the quantum hardware or the quantum computing is mainly relies on how many qubits you are going to realize out of this the computing capacity or GPU, whatever you are using. You have a better number of qubits with a less amount of noise and the good error correction. You can have a better accuracy and better computing. But if you are limited by amount of the qubits you can simulate, in that case the accuracy may go low because you have to redo the same calculations by realizing different qubits through this GPU. Okay, so one thing you can compare when it comes to classical algorithms to quantum algorithms, one is accuracy. Let's say the computing capability is there, GPUs are there, accuracy you can check. Another one is how much is the loss, the errors, duty errors, that you can check. So in that way you can test your quantum algorithms, whatever is there available on the cloud. Okay, as such there is as per my knowledge goes, there is no specific tool. Okay, right. Is there any relevance of quantum computing with respect to lightning strikes? Lightning strikes. I think it's the same question was asked again. I think you mean during the rain, the lightning would happen. That is the thing you are asking. I feel it's like a charges being interacting. I think that is going to give you a sharp spike in the energy. I think that is the lightning. Of course, there is an interaction of quantum particles there, but as such, there is no relevance to quantum computing in our case. But that's a different. That's another different physics concept. You could check. I think I'll check sometime later. I can come back to you on this specifically in one-to-one manner, how the lightning happens. Okay, but it has no relevance to the quantum computing. Okay, then I'll get back to the PPT. Okay, then here you can see quantum computing demands this ordinary differential equation. Why? Because there is eigenvalue equations. Okay, whether H takes operator form or E takes an operator form, I end up with the differential equations. I have to solve them. Okay, so that's why I need to know how to solve the differential equations. Okay, and when it comes to evolve the system, okay, right, now get back to the notes and show you what I mean. Okay, let's say take initially atom is in the ground, means electron is in the ground. So the quantum state is, initial quantum state is 0 ket. Now I want to put that electron into superposition state. Now the question is how to put the electron into a superposition state. Okay, right? Straight away you would say, as now you have gone through first module, you would say, please add the Hadamard gate. What is the Hadamard gate? Hadamard gate is 1 by square root of 2, 1, 1, 1 minus 1. Okay, answer. Hadamard action on the quantum state 0. Okay, H acting on psi 0 gives you, H acting on 0 gives you 1 by square root of 2, 0 ket plus 1 ket. Straightforward. That is the answer you may give. But please remember, on paper it's a Hadamard gate operation, but when it comes to, okay, when it comes to reality, like say experimental case, what is the Hadamard gate correspond to? Hadamard gate correspond to a pulse of pi pulse or pi by 2 pulse, okay, which has having a sequence of photons separated at some time difference. What is the time difference is? Let's say electron is initially in the ground, one photon is having a difference of energy equal to the separation of this atomic levels, that one photon pushes the electron to the excited state. Now that electron remains there for 1 microsecond, 10 to the power of minus 6 seconds. Okay, after that it comes back. By the time it comes back, I'll send one more photon, means I'm separating 1 microsecond apart on another electron. So in that way, what I'm doing, I'm making the electron to do the hopping between ground and excited, just like I toss a coin. Coin is being excited like a head and tail in both the form. So in this way, I have a pi pulse which is going to put the electron into superposition state. Okay, so on a block sphere, you might have gone through now, block sphere. Okay, initially the quantum state is in the north pole. Okay, the quantum state is actually pointing towards the north pole. Now I have to rotate that to equal superposition state, which is 0 plus 1 ket divided by square root of 2, which is along the x direction. Okay, this is x, y and z. Okay, so what should I do? I have to rotate it by pi by 2 angle. So rotation by pi by 2 I have to do. So that rotation about the y-axis with a pi by 2 angle is done with a pi pulse, or you can say now pi by 2 pulse. So it rotates about 90 degrees. Okay, now that is actually a sequence of photons placed some 1 microsecond apart, roughly speaking. Okay, now that is in the reality. So Hamiltonian, question is, who gave you this expression for Hamiltonian? How to get that? By the way, the quantum state old, if I know, I act a unitary operator, I get a new quantum state. Let's say new. Okay, so this is old state is 0, new state is 0 plus 1 divided by square root of 2. This is what I have. Now the question is, what is that u? Unitary operator. By the way, I just earlier derived unitary operator is exponential minus I by h cross Hamiltonian multiplied by t. Okay, or if you want, t minus t naught. Okay, from some t naught to t final, I am creating evolution of the system. So let's say if you take a t naught equal to 0, if t naught equal to 0 and tf is some t, in that case, unitary operator which pushes the system from some time 0 to time t is minus ih cross by Hamiltonian multiplied by t. Now, I know the unitary operator, which is a Hadamard matrix. Okay. Now, what is the corresponding Hamiltonian? Okay. What you can do? You can just simply take the log. Take the log of this entire equation. Okay. What happens? Right hand side becomes Ia by h cross Hamiltonian multiplied by t log of 1 by square root of 2, 1, 1, 1 minus 1. Okay. Now you get the Hamiltonian, which is equal to, okay, this becomes ih cross by t log 1 by square root of 2, 1, 1, 1 minus 1. Okay. This is the corresponding Hamiltonian for a Hadamard gate. Okay. Remember, for every gate operation, there is a Hamiltonian. So basically, Hamiltonian is that defines about the system around. Okay. And remember one more thing. Hadamard gate, what is 1 by square root of 2? Okay. Which I can write down as 1 by square root of 2 as 1 minus 1 plus 0. Okay, what is this? 1 by square root of 2 z gate plus x gate. So, Hadamard gate is just the sum of z gate and x gate divided by 1 by square root of 2. Okay, I have inside a h gate or Hadamard gate, I have a x gate and z gate. Sometimes people write x gate as a sigma x and z gate as a sigma z. That is a Pauli x and Pauli y, Pauli z. Okay, this is a Hadamard gate. Now the question is, how can I create the gate operations by the Hamiltonian corresponding to the gate Hadamard? Similarly, what is the gate correspond to x gate? Simply, you replace h cross by t log. What is the gate for x? Is simply 0, 1, 1, 0. Okay. So I got Hadamard gate required, Hamiltonian required to create a x gate operation on a given quantum state. Okay. Similarly, for a y gate, what is the Hamiltonian? Ih cross by t, ih cross by t log of, okay, for a y, what is the matrix? Matrix is this. Okay. So the moment I know the Hamiltonian, you can find the corresponding unitary operator, because I know unitary operator is simply exponential of the Hamiltonian multiplied by the corresponding factors like I, T, and Planck's constant. Okay, right? So now coming back to the notes, PPT. So if I want to design a quantum gate, okay, so I would be defining a Schrodinger equation where the Hamiltonian is there, means which is describing the situation. Whatever the situation, it is going to embed a x gate operation or a y gate or a z gate operation. So I can design the Hamiltonian according to that. You see, right? So sometimes I may not succeed in designing the exact Hamiltonian. So what I do by trial and error method. First, I create some Hamiltonian and see what is the effect it is going to create on the system. Whether the right effect is obtained or not, I'll just find out, and from there I will just do the error analysis. Means how much error I created with the initial creation of Hamiltonian. Okay, this next time I have to reduce the error. I just tweak the parameters little bit inside the Hamiltonian. That I will show you in the next slide. Okay. Okay, I think where it is, it's next to next slide. For the time being, let's go one by one. Okay. So by knowing the Hamiltonian, you can know what is the unitary transformation, which is going to show you change in the system. Okay, right? So the next thing is error analysis. You can do the modeling noise and decoherence involved in the system using something called master equations of Lindblad form. What I mean by that is, right now we have a master equation IH cross dou psi by dou t is equal to H psi. Okay, right? So in fact, if I write it in the Ket form, it is much easier to understand. Dirac Ket. So when I take a collection of quantum systems, not all will behave in the same fashion. Some behave in a slightly varied form. So you have a mix of different quantum systems. So there is a group of quantum systems behave like one way. There is another group slightly deviating. So in that case, I have a dense of quantum system, which is represented by something called density matrix. So density matrix rho is, there is a group of quantum systems exist with the probability P1. So psi 1, psi outer plus psi 2 outer. Similarly, I have up to psi n. Okay. So these are group of density matrix, the group of individual groups, atoms behaving. So in this case, now what happens to this state equation or eigenvalue equation? It simply becomes a Lindblad form, which is radiation of quantum system overall dou by dou t is equal to minus I by h cross. There is something called commutator rho into h. Commutator rho into h is rho h minus h rho. Okay, Hamiltonian. Remember, it is Hamiltonian. Okay, right? So this is a Lindblad form when I talk about the quantum systems being in a mixed form. Okay. Now, when I have a mixed form, there is something called a noise also comes into the picture. The decoherence also comes into the picture. That is explicitly written in the form of Lindblad operator, which is minus with a calligraphic L acting on the quantum state. Means there is a decoherence. Okay, there is a decoherence can happen by reducing the lifetime of the electron in the excited state. And also the polarization also decoher, means the oscillations may not sustain for a longer time, it may reduce in time. So the lifetime of the excited state also may reduce, the lifetime of oscillations may also reduce. All those things are captured in this calligraphic L operator acting on the rho. So that is the Lindblad form of a mixed quantum system. That is what I was referring. So in that way we can model even by capturing the entire the variation in the quantum systems. Okay, while doing error analysis you will do that. Okay, now when it comes to solving, either you can use RK4 method, okay, Runge-Kutov method, okay, and you can use something called Monte Carlo integration. Okay, we'll just discuss this explicitly tomorrow. What is RK4 method? What is Monte Carlo integration? And there is something called split operator method. Split operator, we already tried to do it earlier. Now, as we know, Hamiltonian involves kinetic energy plus potential energy. 1 minute. Kinetic energy plus potential energy. You can separate them into two different sets and then solve them. Okay, and then later you can add them up. Okay, so you might use something called a fast Fourier transform, FFTs. to accelerate for multidimensional problems. Okay, right? So multidimensional in this case, not only X, Y, and Z, there will be rotational dynamics, there may be spin dynamics, all those things will be there. So in that case, the solving differential equations may not be that straightforward. So you can use something called fast Fourier transform there. Okay. So the matrix exponential methods already I just gave you how to find the corresponding Hamiltonian for a required gate operations. Okay, right? So let me go further. Yeah. So the practical applications, if you see, right, by knowing solving this differential equations in quantum, what you can do, you can just do a circuit simulations. Okay. For example, if I have a n qubits, how to simulate, okay, state vector evolution of through gate operations. Okay. And a 20 qubit circuit requires how much? About 1m complex numbers, okay, with billions of operations, right? So it's becomes much easier if you know how to deal with these things in the quantum computing. Okay, and for example, control pulse optimization. Okay, so there is an algorithm called a Grave algorithm. It iteratively designs optimal pulse to implement target gates which can achieve up to 99.9% fidelity through gradient based numerical optimization integration. Okay, right? So I start with some Hamiltonian which may not be accurate. So what I will be doing, let's say I want to achieve a quantum state psi final. Okay, but I am starting with psi initial. Means I had a quantum Hamiltonian defined, acted on some psi of 0, and I obtained this one. Whether how close this initial to the final, I can find. Okay, I can find the closeness through something called fidelity. Okay, so I have it somewhere here. Where do I have? Yeah, here. Here you see the inner product between the target state to the initial or the final state to the target state. So I started with something, I reached to some final state. Whether that is the target state or not, I should check. So how close they are, I'll just take inner product between them. If both of them are same, I'll get one inner product. If the fidelity anything close or more than 0.99, I have done the job for us. Okay. So in quantum computing, there is something called variational algorithm. What is the variational algorithm? Yes, as per our Hamiltonian, let's see here, specifically for X gate, Y gate, and Z gate or Hadamard gate, I can define a corresponding Hamiltonian. It is straightforward. But the question is, some peculiar gate operations I want to get. Not only this, maybe a combination of all of them. Okay. So what is that kind of example? I have it here. Okay, you see here there is a system Hamiltonian, okay, which consisting of Z gate operation, which consisting of X gate operation and Y gate operation. So all together defines some gate operations, okay, which is represented by some Hamiltonian. Okay, now you see this Hamiltonian depends on not only the X gate and Y gate and Z gate, it also depends on factors like capital omega t. It also depends on angular frequency. Okay, let's say some kind of a pulse is coming. What is the frequency of the pulse? Okay, the pulse is having some amplitude, so that amplitude may be this capital omega t. Okay, so likewise there are so many factors are there, so H is depending on all those factors. Now I'll just start with some optimal value and act on the quantum state. I evolve the quantum state to some final quantum form. Whether that final quantum form is exactly same as the target or not, I just checking at every instant of time, every iteration. If the fidelity is less than some threshold value, I'll just redo. Next time while I'm redoing, I'll change the omega value, capital omega value, by small values and see whether the fidelity is going very far from required value or going close. When it is going very close, I'll tweak little. So by trial and error method, by some conditional logic, I can do this. So this is going to defined as variational algorithms. Okay. So there, every point of time, I'm going to find out what is the expectation value of this designed Hamiltonian on the quantum state. Expectation value means I act on the system and see what is the expected value. Several times I act on the system means doing the same experiment several times and average out the value of output. So averaging out is actually the mean value. So when it comes to quantum computing, it is called expectation values. It's basically mean output of several iterations. Okay. So this is how I'm going to get the exact required quantum gate from the initialization of the quantum gate. So you are not going to hit the right quantum gate in a straight away. So you have to start from very small iterations. Okay. So while doing it, you might even change the quantum states also, since the quantum states evolve from zero state. Okay. We have it right earlier. I showed you. See, initially quantum state is there. Later it evolves to some superposition state. Okay. Right. So in the Hadamard gate, this is the case. But in other complicated quantum operations, I need some quantum output state, which is as per the requirement, as per my applications. Okay. Right. Now let me go further. Noise modeling, I just already gave you Lindblad form. Okay. Right. Yeah. I already gave you a Lindblad form already. So I'm not going to detail. Yeah. So yeah, numerical integration. Okay, that the people talking about RK4 method. So to start the RK4 method, I need to introduce you numerical integration. So probably I'll do it tomorrow. What is the numerical integration? Okay, right. Here, core differential equation. What are involved in our case? Second order linear differential equations or ordinary differential equations with a constant and variable coefficients. Both are there in our situation. Okay, right? And which is actually eigenvalue problem or Stern-Liouville theory based on that. And there is a boundary conditions involved, like say quantum states. Just a minute. The quantum states are going to vanish at the boundaries. So that is what the boundary conditions. So we need to use them. And whenever I have a problem in solving as such, what you can do separable method, separation into radial direction, separation into x, y, and z into each dimension. In the case of Cartesian coordinate system, in the case of spherical coordinate system, what you can do, radial, angular, and if there is any other dimensions like spin dynamics, even in that case, you can separate the differential equation and solve it. Okay, right? So that is a basic analytical method you would be doing on paper. Okay, but when it comes to numerical integration, there is something called Euler method. Okay, and Euler method is not that accurate, so there may be some corrections are involved required to that. So that is called Euler. The Euler is corrected by some new method. So after that, you can go and come up with something called RK2 method. Okay, right? So yeah, RK2 and RK4 method are there, and then the fast Fourier transform FFT, and there is a Monte Carlo integration, and there is a finite difference and spectral methods. So these are all available on the cloud or any programming toolkit. If you just take, it is has either MATLAB or a Mathematica, or you can take a Python. All of them are equipped with these toolkits or these functions or subroutines. Using them, you can solve. Okay, right? And okay, so what are the linear algebra assumptions you need to use or you need to understand to do all these things? Matrix operations, as usual, a decomposition of a given a given matrix into its eigenvectors and eigenvalues. That is called a spectral decomposition. Okay, and eigenvalues and eigenvectors problems you should be knowing, and unitary transformations. Okay, in the case of quantum information, and you would be knowing you should be knowing tensor products. Okay, right? And a singular value decomposition means a given matrix can be decomposed into its diagonal matrix and eigenvector matrix. So that is a SVD for you. And you need to know some complex analysis also, right? Okay, and some probability and statistics are required. So these are the mathematical toolkits are actually involved in understanding solving the quantum dynamical system of equations. Okay, so the toolkit summary for you. So let me take one question here. Okay, there is a question. Is there any model which gives NMR spectroscopy converts into quantum where Google used in below? NMR spectroscopy converts into quantum where Google used in below. Okay, right. So if you can check how NMR based quantum systems are used to do quantum computing. Okay, so there is a mathematical modeling is discussed in this journal papers. So to start with, you can check ISER Pune, Professor T.S. Mahesh research papers. They are working on NMR based quantum computing for the past few years. Okay, so you please check Professor T.S. Mahesh paper. There definitely in some paper they might have discussed the theoretical modeling of their quantum qubits realized out of NMR based systems. Okay, right. So let me see another question. Okay, there is a Lakshmi Narasimha's G's question. Can you please let me know what extent these equations and derivations are required while applying quantum computing as end user? You have already mentioned, but I could not follow. Just to correlate, can you please cite few instances where in which we will use these equations? Then what is the role of SDKs like Qiskit, Bracket, and Pennyline, etc.? Okay, so come back to here. Okay, maybe I can start from here. You see, I want to have a gate operation. Okay, I want to evolve some quantum system, some psi initial to psi target. Okay, right? I want to evolve the quantum psi initial to psi target. For sure, I know there is a unitary operator that pushes the quantum system psi initial to psi target. Okay, right? So on the right hand side, you see the eigenvalue equation, which tells me to have such a variation, I need to know the corresponding Hamiltonian. Okay, how do I define that Hamiltonian? Okay, basically to get to know that Hamiltonian, either I solve the differential equation involving initial state and later state, and having solving the differential equation, I would know what is the corresponding Hamiltonian which does such thing. Okay, so answer to your question, I first should know how to find the evolution from some value, some form to some other form by creating what kind of environment. What kind of environment creating on paper is finding out the Hamiltonian, which is having so many gates and so many other parameters. Okay, so basically you are going to create a quantum circuit involving X gate and Y gate and Z gate, some other factors coming into the quantum circuitry. So you are going to test it initial stage, whether you got the final quantum state or not. If you got, fine, you will stop at that quantum state. Otherwise, you just tweak the quantum circuit again a little bit and then evolve. So when it comes to design the quantum circuit, you should know what is the evolution which does that change. So okay, so yeah, that's the answer for your question. You need to define the Hamiltonian. To define the Hamiltonian, you need to know how to solve the differential equation. From there only you get the Hamiltonian description. Okay, so when it comes to this toolkits like Cascade and Penny Lane and all these things, you remember when I call the function of Hadamard gate, when I simply call the function of Hadamard gate acting on some quantum resistor, behind the subroutine, behind that function, okay, the what which equation is involved? This gate operation equation is involved. Okay, where is that? Okay, so such gate operations are involved behind that. Okay, so you want to have a combination of X gate, Y gate, and Z gate. In what form? With some parameters multiplied to X gate and Y gate and Z gate. So accordingly, the gate operation has to be formed. Then what you will do? You simply pick the X gate and Z gate and put it on your register in the KISS gate. But what goes behind? This mathematics goes behind. Okay, so since the toolkits are already equipped with everything, the ready-made things are there, so no need to bother about what is the background. Let's say you want to come up with your own toolkit, okay, which is much superior or which is customizable as per your requirement. In that case, you should know what is this mathematics involving it's involved in defining the quantum gate operations. That's why we are getting into it. Okay, so not only somebody designed certain quantum circuit, okay, hardware wise, okay, nobody is going to stop at that point. Let's say people initially came up with the called ion traps, okay, ion trap based quantum computing or neutral atom based quantum computing, and these days the photonic based quantum computing, and the most explored one is superconducting qubit quantum gates. Okay, so in all those cases, how to manipulate them is described by Hamiltonian around them. Okay, how to know what is the corresponding Hamiltonian? Okay, we will find out how it is evolving. By knowing how it is evolving, what is the corresponding unitary operator we will get. From unitary operator, you can make out what is the corresponding Hamiltonian. Okay, reverse fashion. If you know my Hamiltonian, you can define the unitary operator. If you know the unitary operator, you can come up with the Hamiltonian. Okay, so that the theory, the behind the screens people call, that is what we are discussing today. Okay, fine. So yeah, the role of Qiskate and SDK, all these things are the penny lane. They're already ready made. You can just go and use it for yourself. Okay, right? Now, if you want to come up with your own, you should know all these things. Okay, then what? Okay, what is the role of fast Fourier transform in quantum computing? Is it the same what we practice in digital signal processing or something different? Exactly, it is very close to that. Okay, whatever Fourier transform you do in conventional signal processing, so here there is something called quantum Fourier transform, QFT. Okay, so in the signal processing case, you are moving from time domain to frequency domain. Okay, you capture all time domain data into few frequency points. Okay, let's say frequency peaks. Fine. So here in the quantum computing case, quantum Fourier transform is nothing but, so quantum state is usually represented by what? Okay, let me use my hand notes. So quantum state is usually represented by some alpha 0 plus alpha 1. This is qubit. Okay, so I can transform this into some other new quantum state. Let's say some psi nu, which is going to represent it as some beta 0 plus gate, beta 1 minus gate. Okay, basically this is also qubit, or it is in the new basis states, plus gate and minus gate. First one is in computational basis, described on 0 and 1. Second one is described on plus gate and minus gate. Okay, right? I'm going from one basis to another basis using a Fourier transform, which is a quantum Fourier transform for you. So the moment you do a Fourier transform, the calculations becomes much more faster. By doing quantum Fourier transform, you can do much faster. So fast Fourier transform is something of that kind. Okay, yes, there is a possibility of FFT even in the quantum case. Okay, right. Yeah, so I'll definitely share my this notes as well as the PPT. Okay, right. So there is a question by Jagdish Ji. I am electrical engineering background. Okay, he is from. I want to work on large scale fault tolerant quantum computer for novel design of highly reliable quantum secured microgrid networks. Is there any reference book I can follow? What all concepts of quantum computing is relevant for my research work? Okay. So to start with, you can there is two books. One is Nielsen and Chuang. Another one is the fundamental books I'm talking about. I think another book is I'll share both the books. Okay, through Canvas in my folder. You can check those books. But when it comes to applied, I think you need to check a specific applications. Okay, for example, fault tolerance quantum computing. There are multiple ways in theory you can try fault tolerance quantum computing. Okay, so there is something called Hamiltonian based quantum computing fault tolerance, and there is something called uh, frequency, sorry, noise-free frequency subspace-based quantum computing. Okay, so there are various ways you can try. So for that, I think you need to dig a little bit deep in advanced uh, research. I would say instead of looking at the reference books, you can check on the journals. Definitely, there are very good research articles in this direction. You would find. Okay, yeah. Is there, okay, Hadamard gate is a quantum Fourier transform gate. Absolutely, Durgeshi. Perfect. Okay, so in fact, Hadamard gate is the first order Fourier transform from going from 0 gate, 1 gate to plus gate and 1 gate. Absolutely. It is also referred as a Welsh gate. Welsh gate W0 is just to identity. Welsh gate of first order is Hadamard gate. Okay, and even I can come up with the Welsh gate of second order, which is, remember, W1, W1, W1 minus W1. I think there is a factor of 1 by square root of 2, 2 is that. This is the Welsh gate of second order. So Welsh gate of nth order, you can get it from Welsh gate of, sorry, n minus 1. Okay. You see now, Welsh gate of first order is what? 1 by 2 to the power of 1, 0, 0, V of 0 minus V of 0. What is this? 1 by square root of 2, 1, 1, 1 minus 1. Okay. Now, what is the second order Fourier transform? Is a Welsh gate of order 2, right? So what it does? It probably moves quantum state 0, 0, 0 ones, 1, 0, 1, 1. It moves these things to plus, 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 minus, minus, plus, minus, minus, something like that. Okay. So this is a Fourier transform, quantum Fourier transform. Okay. Right. Okay. Then other transforms like DWT also will use here. I doubt. Okay. So as of now, up to the Shor's algorithm, Fourier transform is enough, quantum Fourier transform. Okay. And 0 ket to plus ket, 1 ket to minus ket is a Hadamard gate. Yeah, that is, you might have seen in the first module. 0, Hadamard acting on 0 gives you plus ket. Hadamard acting on 1 gives you minus ket. Even you can go back. Interestingly, the inverse Fourier transform in the quantum computing is the same. Okay. Why? Because you see, unitary operator multiplied by dagger gives you identity. Okay. Right. So having Hamilton Hadamard gate acting on 0 gives you plus ket. You do one more time. H acting on 0 twice is H acting on plus give back the same 0. Okay. So the inverse Fourier transform is also same. So that is the beauty of quantum computing. You can have most simplified versions here. Okay. Fine. So let me conclude for today, and then we will come up with the numerical integration tomorrow. I'll show you some simple programming toolkits or programs, simple programs, how to do numerical integration. Probably you might have done it, but anyway, for those who have not done, for them I'll show. Okay. So to start with for today, okay, right? So dynamical features in quantum systems. Okay, so to understand that, we started with a qubit. Okay, qubit is going to have some kinetic energy and potential energy. Okay, which is in fact varies in time and space. Okay, let's say there is no potential energy, okay, or there is no kinetic energy, how to deal those things. For example, for a quantum system exposed to some potential energy oscillates like a spring mass system or oscillates like a pendulum. In that case, what is the kinetic potential energy definition? Okay, so how to solve this dynamics or dynamical nature from the eigenvalue equation? We saw that. Okay, so basically it involves some unitary evolution represented as a unitary operator action. Okay, so different scenarios, how to solve the differential equation, and we get to see the nice interesting behavior where the energy of the systems behave differently. Okay, so when the case of no potential energy, I have wave nature. When in case of potential energy also have another wave nature. It's slightly different with different energies. For the hydrogen atom, how to solve also dynamical systems we saw. Okay, right? And when it comes to defining the required gate operations from the Hamiltonian, we know that. Corresponding gate, what is the corresponding Hamiltonian? Or knowing the Hamiltonian, I can define the gate. How did I get? Actually, from the differential equation solving only, I get to know that. Okay. So, like a conclusion for the overall thing is, basically the unitary evolution is nothing but some Fourier transform kind of an action. Okay, right? Hadamard gate operation is a first order Fourier transform. So in the PPT also we saw that systematically from the starting. Okay, right? So from the starting, the dynamical system is represented by Schrodinger equation, either time dependent or time independent, depending on the situation or depending on the resources I have. Okay, particle with no potential inside a box, particle with some potential inside a box. It's also a harmonic oscillator. Okay, particle in an hydrogen atom or an electron in a hydrogen atom. What is the dynamical scenario? Okay, how to solve them? So it is not only confined to quantum physics, it is there everywhere. So that was actually listed on my figure on the left. Okay, what else we can do here? We can solve them using various methods, starting from numerical integration and actual integration. There is a critical reality here. Most of the quantum systems have no analytical solutions. That's why we have to rely on numerical integration. So like RK4, Monte Carlo integration we will be doing. Okay. So what are the practical applications? Here I can design the circuit, I can define what are the Hamiltonian required to create some gate, and by doing it you can do some variational algorithms, exact gate operations you can come up with by trial and error method. Okay, and some particular case study for superconducting qubit gate design. So where let's say this is a gate Hamiltonian which is going to implement the combination of gate operations. Okay, so how do I do that? I can just implement in the right hand side and then see the final output whether it is a target or not. Okay, fidelity. And when it comes to understanding all these things, what are the tools you need to know? There is a differential equation mathematics, you need to know how to solve them. Numerically, you need to know. Some linear algebra, you need to know. Some complex analysis, you need to know. Probability statistics, very basic. Okay, right? And software tools are already, most of you are already exploring. These things are available on the cloud. Okay, so takeaway is quantum mechanics is differential equations involving. So it is going to be the bedrock for the quantum computing that we explored today to a certain extent. Tomorrow we will just see how to implement on classical computing and then go on to quantum computing. Okay, I'll stop at this point. Okay. So if there is anything you can ask tomorrow also, we'll discuss tomorrow also.
Thank you so much, sir. Participants, if you have any question, you may put it in there. I think plenty of discussion has already been done. But if you feel any question, you may ask.
So I'll be sharing both my hand notes as well as PPT in the canvas. Okay, there will be a canvas for you, I think, for this QT module. So in that it will be shared. Okay, some references also I'll share. Okay, so see you everyone tomorrow. Bye bye for today.
So thank you, Dr. Aswat, sir. And from beginning, sir has already covered the mathematical foundation of quantum computing, and I hope the amount of discussion, including the Hamiltonian operator and this Fourier transform and quantum, the relationship between quantum states and energy levels, I think that were quite in depth. So I hope the for future sessions will also be interesting. And thank you so much, sir, and thank you all the participants who have been engaged in the session throughout the session. Thank you so much.
Because sir, thank you, sir. Sir, please do share this canvas link. I'll upload my both the notes today.
Sure, sir. Sure, sir. Okay, okay, sir. Thank you so much, sir.
Okay, sir.
Thank you all the participants. Bye, sir.